Hi, my name is Lucas Joppa. I'm a scientist in the Computational Ecology Group here in Microsoft Research in Cambridge. And in the Computational Ecology Group, I like to think that we work on the science, policy, and tools and technology necessary to sustain Earth's life support system. But what I want to talk about today is just a subset of what we're working on in the group. And that's an initiative called Technology for Nature, which is a collaborative initiative between Microsoft Research, Zoological Society of London, and University of College London. And what Technology for Nature is all about is using innovations in technology to rapidly scale up the conservation response to the loss of biodiversity. And we're doing that through creating novel data collection devices, sensors, to really try to enable a ubiquitous computing of the environment so that we can understand what's going on out in the natural world and immediately respond to things when they go wrong. So we're doing that in two particular ways. I just want to show you a little bit of the technology that we have running on this plinth here in front of me. The first is a whole bunch of stuff that we've built with a platform called .NET Gadgeteer. .NET Gadgeteer is fantastic. It's really like a building block sort of platform for building any sort of electrical devices, sensing devices that you can imagine. I've plugged a couple things together here. Here's a weather sensor. If I lick my finger, for example, and place it there, it'll start recording continuous humidity measurements. I've got a camera pointing at me here. I've got a motion sensor, a PIR sensor here, and I've got an LED display right here. So if I stand here and I wave my hand in front of the sensor, you can see that my picture's been taken and is shown on the display and saved on this SD card here. And the critically important thing about all of this is that we built that system in about 5 minutes. We plugged together the little modules and devices, we wrote a few lines of code, and we're off and running with a deployable kind of device. Another thing that I want to talk about is a device called Mataki, which is a really small, lightweight, cheap, and power-efficient GPS tracking device that animals can wear around in the wild. And critically, it carries some software on there called Informant, which sets up a mesh network across all the animals that are carrying this device within a system. And so this device here can download data from remotely, from up to 1,000 meters away to a base station. But for certain large animals like elephants, the guy staring at me from behind here, they range so far that we don't actually know where they're going to be going to within a nearest kilometer to go and get their data. And so we're starting to put these sorts of devices as payload on unmanned aerial vehicles or drones. So I've got a quadcopter here, and you can see if I flip it over, we've got two devices. We've got a .NET Gadgeteer enabled radio device here, and we've got a Mataki device here. And so whether it's on this quadcopter or on that large fixed wing drone over there, these unmanned aerial vehicles can fly around and listen for the presence of these devices. And when they hear them, they can fly over there, they can switch their autopilot mode to the device itself, and suddenly you have actually an elephant-driven drone, right? As the elephant's wandering around, the drone's following it and taking high-definition video imagery. And so the issue about that high-definition video imagery is pretty important, because no matter how cheap we make these, we're not going to get them on all the elephants out there. And so really what this does is it takes long-term, from a temporal perspective, data on where an elephant is, and then in the short term we can have drones flying around taking video imagery to figure out what all the elephants around that other one are doing as well. But of course that means that we have to extract the information, the tracked information from those other elephants that aren't wearing our devices, from video imagery that's collected from the drone. So I'm going to show you just a bit of early version software that we've used to do just that. I couldn't put elephants in a box, and I was interested in doing a bit more of a laboratory style experiment. So instead I put some bees in a box, and they're flying around and choosing between white and purple and white flowers that they want to feed from. And I just want to show you really quickly how easily the software allows you to extract tracks from images. And so you can see this bee flying around here. It's really hard to actually even determine that it is a bee, it's going so fast. But you can see that if I say, okay, I'm going to call this the first frame, and I'm going to click on this bee here, which is really just a blur in the imagery, you can see the software immediately makes a mistake. But if I then go to the end and I click on the bee again, you can see the software immediately makes another mistake. But the really nice thing, and this really exemplifies what in the computer science world we call human-in-the-loop interfaces. You can see if I scroll this back here, and I just give the software a little bit more information, you can see in 3 clicks, I managed to extract the entire track of that single bee. And so in that way, using that sort of software, we can connect these on-the-ground devices through radio transmission to vehicles flying around in the air, collecting video information, and then again extract those data from animals that aren't wearing these particular devices. And it really does allow us to extract the data from these sensing devices and start to confront the models that we're building in the computational ecology group. And that's how we're going from small devices like this that animals are wearing out in the wild, communicating wirelessly to flying vehicles in the sky, which are taking high-definition video imagery. We're extracting those data from what we're trying to build of an ubiquitous computing environment. We're extracting those data, using those data to confront the models that we're building in the computational ecology group. And from those models, we can then ask whether or not they actually replicate the world as we know it, and if so, then we can have a measured amount of confidence in projecting those models forward. So what I hope you can take away from this is a better understanding of how we in the computational ecology group are marrying up the technology with science in order to enable people to make robust decisions about how we should best manage the future of life on Earth.